Bismillahirrahmanirrahim. In the previous lecture, we were talking about polynomial equations. We have written some expressions for the polynomials, and then we have defined the polynomial equation, the general form. Then we have talked about the solution to the cubic equation, and we have given the full procedure. Now I will talk about how we solve, or like, is there any solution to the higher degrees? So for the higher degrees, we know that not long after the solution of cubic equations, Ferrari, who was a pupil of Cardan, who gave the solution for the cubic equation, showed how to obtain a formula for the roots of generic quadric. So we can note that Ferrari, a pupil of Cardan, one who gave the solutions for cubic equation. Ferrari was a pupil to Cardan, and Ferrari showed how to obtain a formula for the roots of a generic quadric which is degree 4 equations. Then next step, naturally enough, was quantic. However, several hundred years passed without anyone finding a formula for the roots of generic quantic equation. So no generic formula for the roots of quantic equations. There was a good reason for this. There is no such formula, nor is there a formula for equations of degree greater than 5, nor the equations of degree greater than 5. This amazing fact was established in the early 19th century by Danish mathematician Abel. So Abel, a Danish mathematician, who died at age of 26, said that there is no formula to find roots of degree of equations degree 5 or greater than 5. After which the Frenchman Galios built an entire new theory of equations. So Galois, a Frenchman, built an entirely new theory of equations, linking them to the then recent subject of group theory, linking them to the recent subject of group theory, which not only explained the non-existence of a formula, but laid the foundations of whole edifice of algebra and number theory known as Galois theory. So, which not only explained the non-existence of formulae, but laid the foundations of a whole edifice of algebra and number theory. And if you combine them, you will have a new subject called Galois theory. And this is a modern area of research. Hopefully, if you get the chance, you should take a course in Galois theory during the rest of your studies in mathematics, and you won't regret it. After this, some history, we can talk about the famous Fundamental Theorem of Algebra. So there is no formula for the roots of polynomial equations of degree 5 or more. We are therefore led to the troubling question: can we be sure that such an equation actually has a root in the complex numbers? The answer is to this question is yes, we can be sure This is a famous theorem of another great mathematician, perhaps the greatest of all, Gauss. So you can say this was given by Gauss, and the theorem says which we call it 7.1, Fundamental Theorem of Algebra, that every polynomial of degree at least 1 has a root in complex numbers. This is really a rather amazing result. After all, we introduced complex numbers just to be able to talk about roots of quadratics like x squared plus 1 is 0, and we find ourselves with a system that contains roots of all polynomials. There are many different proofs of the fundamental theorem of algebra available. Gauss himself found 5 different during his timeline. Probably the proofs that are exist easiest to understand are those using various basic results in the subject of complex analysis, and most undergraduate courses on this topic would include a proof of the fundamental theorem of algebra. In chapter 24 of this book, and then in this lecture series, we shall give a proof of the theorem for the real polynomials of odd integers. And the fundamental theorem of algebra has many consequences. We shall give just a couple here. And we say that let P of x be a polynomial of degree n. It is rather easy to see from this, but we won't prove it here, that there is another polynomial q of x of degree n minus 1. So there is another polynomial q of x of degree n minus 1 such that P of x can be written as x minus alpha 1 into q of x. And by above theorem 7.1, q of x also has a root in complex numbers, and we call it, say, alpha 2. So is above, there is a polynomial r of x of degree n minus 2 such that you can write P of x as x minus alpha 1 into x minus alpha 2 into r of x. And we repeat this argument until we get down a polynomial of degree 1. Until we get a polynomial of degree 1, then we get this. Then we have that we can write P of x is the product of a into x minus alpha 2 product so on x minus alpha n, where a is the coefficient of x power n and alpha 1 to alpha n are the roots of P of x. These may, of course, not all be different, but there are precisely n of them if we count repeats. So by this, we will give another proof. Another theorem says that, and this is 7.2, says that every polynomial of degree n factorizes is a product of linear polynomials and has exactly n roots in complex numbers. Now this is a simple fact we learn in the first year 11 or year 12 courses, but like the history behind it, how did you know this? This is the way we know this. Next, we briefly consider real polynomial equations, that is, equation of the form. So let's say next we consider real polynomial equations of the form that P of x can be written as an x power n plus an minus 1 x power n minus 1 plus so on a1x plus a naught is 0, where all the coefficients are real numbers, where an a naught a1 up to an they belong to real numbers. Of course, not all the roots of such an equation need to be real. So like we have the equation x squared plus 1 is 0. However, we can say something interesting about the roots. What can we say? We say that let alpha is a complex number and be a root of the real polynomial P of x is 0, Thus, if we put this into alpha, then we get an alpha power n plus an minus 1 alpha power n minus 1. Then we get a polynomial in terms of the alpha, which is 0. And now we consider the complex conjugate of alpha, which is alpha bar. We shall show this is also a root. We shall show this is also a root. To see this, observe that alpha square conjugate is nothing but alpha conjugate square. And we know this from the previous exercise. Likewise, we know that alpha cube whole conjugate is alpha conjugate cube. And we can go further up to alpha power n conjugate is alpha conjugate power n. And also ai conjugate is equals to ai for all I. Since the ai's are real numbers, since the ai's belongs to real number, and by doing this, what we get is very interesting. So polynomial of alpha bar is nothing but an alpha bar power n plus an minus 1 alpha bar power n minus 1. And we can continue this up to a naught. And we can also write this thing as alpha power n bar n minus 1 alpha power n minus 1 bar plus a1 alpha bar plus a naught. And we can also extend this conjugation to the coefficients. So an alpha power n conjugation on everything, an minus 1 alpha power n minus 1 conjugation on everything, and so on, plus a naught conjugate. And this is nothing but, if you see this is nothing but p of alpha conjugate, which is 0. If alpha is a root of the polynomial, then it is equals to 0. And if you conjugate the polynomial, then it's again 0. So this shows that alpha bar is also a root of the polynomial, right? And showing that alpha is indeed a root. Thus, for a real polynomial equation, p of x is equals to 0, non-real roots appear in complex conjugate pairs. Say the real roots are, so you can write for a real polynomial equation, p of x is 0. The non-real roots appear in complex conjugate pairs alpha and alpha bar. So say the real roots are denoted by beta 1 up to beta k, and the non-real roots are alpha 1 comma alpha 1 bar comma alpha L comma alpha L bar, where we can complete the number of roots by k plus 2l, which is equals to n. Then what we get? We get that we can write the real polynomial is x minus beta 1 product x minus beta k into x minus alpha 1 into x minus alpha 1 bar product x minus alpha L to x minus alpha L bar. Notice that we can say that product of x minus alpha I into product of x minus alpha I bar is nothing but x square minus alpha I plus alpha I bar into x plus alpha I into alpha I bar, which is a quadratic with real coefficients. Which is a quadratic real coefficients. Thus, P of x factorizes is a product of real linear and real quadratic polynomials. And then by doing this, we have the theorem (7.3), which says that every real polynomial factorizes is a product of real linear and real quadratic polynomials, and has its non-real roots appearing in complex conjugate pairs. So whenever you solve a polynomial equation with real coefficients, you will always get a real linear equation product with a real quadratic equation. And then and for sure that equation will have the non-real roots, but they will always appear in complex conjugate pairs. Imagine a situation where you have an equation, a quadratic equation, which has discriminant less than 0. Then the it will have the what you can call complex roots, and they will always be in a complex conjugate pairs. So there will be two complex roots, and they will be complex conjugate to each other. That is the thing which we wanted to learn from all these three theorems. So this is it in this part. Thank you so much. We will talk about the relation between roots in the next part.